Hello everyone, I'm Lingxuan Tang. Today I will introduce something about quantum key distributions. So, first one, what is the quantum key distributions? What does the quantum key distribution actually look like? We have our usual protagonists, Alice and Bob. They can trust each other, but they don't have access to a secure channel using which to communicate. They know that any message that they might exchange in between them could be potentially be intercepted by a malicious eavesdropper if. What's special now is that in addition to their classical authentic channel, Alice and Bob have a quantum communication channel. They can send qubits to each other using photons. But of course, Eve might still be listening and potentially intercept any qubits that they send to each other. And there is no limit to the power of Eve. You can imagine that he even has access to a quantum computer and can perform any kinds of operation that he wants to the qubit that he intercepts. So what are we trying to achieve here? The first thing that we want, of course, is for the protocol to be correct. So what this means is that whatever happens except with tiny probability at most epsilon, the key Ka that Alice obtains should be perfectly identical to the key Kb that Bob obtains. And how about security? This time we have no guarantees coming from some special channel connecting Alice and Bob. However, the fact that we can send qubits to each other saves us. It should be ignored about key K. What this means is that the joint state of the key and of the eavesdropper system E should be close to the state that E is in a tensor product, uniform from the key and perfectly uncorrelated from the eavesdropper system E. So that Alice and Bob can produce key within a reasonable time frame. So in general, in QKD, the two communicate parties exchange quantum bits through a quantum channel, and they utilize a classical channel to confirm and process these quantum bits in order to eventually generate a shared encryption key. Any eavesdropping by a third party during this process is detected due to the uncountable nature of quantum states and the unavoidable perturbations introduced by the measurement. So let me introduce something, a device-independent QKD. In device-independent quantum key distribution, we will start with a scenario where the state that Alice and Bob share is arbitrary. In particular, this means that Alice may not even have a qubit, but maybe the state rho A is a huge state that has very large dimensions. Also, we will think of Alice and Bob as just measurement boxes that take an input theta A for Alice and theta B for Bob, and produce a measurement outcome XA and XB. But measurement inside can be arbitrary. Device independent is very powerful. We allow any state and any measurement. Any device, even one which is maybe imperfectly implemented, certainly satisfy these conditions. In device independence, we go one step further and imagine that maybe even Eve is one who prepared this device. Eve picked the state and the measurement. Alice and Bob give inputs and obtain outputs from their boxes, but there are still things that even device independence does not allow. Even in particular, it will not be allowed that this device sits sneakily in the middle. Communicate back to the eavesdropper. Device independence is very general, but devices are not completely arbitrary in the sense of that there are no radio inside in device. Not that any device that would have a radio inside could just radio the key to Eve after we complete the protocol, even if the device perfectly implemented the desired measurement and states. It is thus important that Alice and Bob, even though they may not know the device, has them well shared. So let me introduce a famous quantum key distribution protocol, E91 protocol. In general, Alice and Bob literally random choose a measurement ground state to measure the received particles, and their measurement will be highly correlated due to the nature of quantum entanglement. So we usually use the EPR-P, that's the maximum entanglement state. Once the measurements are complete, the choice of basis state is made public via an open classical communication channel, and the measurements in the same basis state are used to generate a shared key. In order to detect potential eavesdropping, the protocol utilizes the Bell inequality test, which indicates the presence of eavesdropping if the measurement violates Bell's inequality. Compliance indicates that the key distribution process is secure. So the E91 protocol may divide it into the 6 steps. The first one is preparation. Generate and distribute the entanglement quantum pairs. That means, suppose Alice wants to exchange an encryption key with Bob. In the first step, Alice will randomly choose a sequence, just a bit streams, how many bits are in this sequence, then how many entanglement quantum pairs are needed. So the second is select. For each entanglement quantum, Alice and Bob eachly random choose one of the 3 measurement directions to measure as shown at the left, and we immediately notify the sum probabilistically the 2 will happen to choose in the same direction to measurement in, while others will not. And the third, they tell each other over a classical channel, for example, phone call, the measurement direction they have adopted for each entanglement quantum, so that both parties know which entanglement quantum measurements are in different directions. A group we denote as G1, and a group with the same measurement direction is denoted to G2. And the fourth, according to the theory of quantum mechanics, Alice and Bob can utilize G1 to perform a CH-SH test, and if it's found that the test value S does not satisfy the requirements, it means that someone is eavesdropping, then the exchange is abandoned specifically. If S is larger than 2, it means that the measurements are consistent with a quantum mechanical prediction and the particle remain entangled. If S is smaller or equal to 2, it means that there may be an eavesdropper and the entanglement set is destroyed. And if the calculated statistics satisfy the requirements, it means that the communication is secure. And the 2 people utilize G2 as the key because according to the principle of quantum entanglement, the measurement of the 2 people should be exactly the opposite. And it's only necessary to reverse the measurement from one side by a periodic agreement. And finally, the key exchange is completed. And the next step is to encrypt and decrypt the data and transmit it over a traditional channel. So for the security of the E91 protocol, they use the quantum measurement as a non-clarity. For the noise or eavesdropping destroy the superposition state, noise randomly changes the state of particle, while eavesdropping forces the particle to collapse to a particular book state. This makes an outcome for Alice and Bob no longer determined by the original quantum correlations, but particularly by classical probability. So how about applicability of the E91 protocol in device-independent scenarios? In general, the E91 protocol has a natural fit with the DIQKD, but also has some limitations. The first one is impact of equipment vulnerabilities. For this means randomness dependency and device trust issues. The IQKD ensures security through a best encrypting violation without the need of trust the device, but relies on random number generated from the randomness can be vulnerabilities. Randomness extension techniques can be generate the longer sequence with finite seeds, but still require initial randomness. So complete the IQKD innovatively utilizes Alice secret message to generate the local random sequence unknown to Eve, thus enhancing the security of the protocol. And the second is the noise and the channel. So for the robust DIQKD, Alice and Bob use uncharacterized device to perform measurement on a quantum state that is created by a source that's potentially controlled by an adversary. In the processed protocol, Alice has two possible input measurement settings: magenta buttons, which are used for the key generations, and for running the CHSH Bayes test, and Bob has four possible inputs grouped into two sets: magenta and Saya buttons. The magenta buttons are used for the key generations, while the Saya buttons are used for the running the CHSH Bayes test. Second is control of the quantum source. That means we need verification of entanglement state under the adversary control. Because if the source of entanglement state is controlled by an eavesdropper, the IQKD needs additional mechanics to verify the validity of the entanglement state. So let me compare the BB84 to the E91 protocol. For first one is secure basis. For BB84 is based on the unclonable principle of quantum mechanics, but E91 is based on the quantum entanglement, and the Bayes inequality ensures the key is quantum in nature or cannot be intercepted or cloned. So the important thing is the level of security. According to the reference 16, the results show that BB84 protocol converts at 50% of the initial key. For keys which are higher than 265 initial bits, the percentage match are the expected theory, whereas E91 protocol is approximate to 20-22% of the initial key for those which are higher than 64 initial bits, which does not match the 33% theoretically accept. So E91 protocol is considered to be safer than the BB84 protocol. And the last thing is the robustness. More robust to some side channel attack secure depends on the non-clonable quantum correlation rather than individual quantum states. That's for the E91. Security is dependent on the state measurement depends and strongly influenced by the physical device and the environment, such as detect efficiency mismatch, faked state attack. That's BB84. That's all. Thank you very much.